We're going to graph this cubic polynomial, and we're only going to use the first and second derivative tests. We're just going to restrict ourselves and see how good of a graph we can get just using those. And so the first thing I'm going to do, of course, when you do that is you need to take y prime, and if you do that you get 3x squared minus 12x plus 9. Now we're going to look for critical points with this first derivative. And the way we do that is we always say, well, what makes the derivative undefined? Well, nothing does. I can use any x I like there. So what makes it 0? That's where we can find some other critical points. And this is just a quadratic, and I have to solve. And the first thing I'm going to do is divide each term by 3 to make it easier to solve. Solve x squared minus 4x plus 3 equals 0. And now I'm going to try and factor it. The factors, then I won't have to use the quadratic formula, will I? And I'm going to do it right here. And it's plus, so it's got minus and minus, and it's x, 1, and 3 equals 0. So clearly we can set this to 0 and this to 0, and we will get the two critical points, x equals 1 and the other one is 3. So I draw my number line, and this is the number line on which I'm going to check y prime. And I've got 1 here and 3 here. And it divides the number line into regions. Let me move this y prime over just a little bit. And I have to check a point. So if I go over here and I put 0 in, that's a nice point, easy to check. I go back to y prime, the original y prime, and I put 0 in, and I get a positive number. Okay, and now I'm going to check maybe 2. And if I put 2 in here, you know, I get 4, I get 12, and then minus 24. It comes to negative. It's going to be a negative number. That's all I have to determine, whether it's positive or negative. And then if I go over here to 4, put 4 in here, see, I'll get positive, won't I? If you figure it out, you'll get a positive value there. This y prime, the fact that it changes from positive to positive, tells us an awful lot about y. For one thing, the graph is increasing, increasing, increasing. It's going up like this, you know, from negative infinity all the way up. And then it's going to have a little max here, because it's flat here, and it starts decreasing, decreasing, decreasing. Continues decreasing, 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 and then it starts increasing. So we have a little min there, okay? So I have a little max, and we have a little min. And so we have, let's see where we can put that. Why don't we just give ourselves some room over, well, I'll give myself some room here, and I'll say at 1 and something, I'm going to have a min, a little relative min. And then at 3 and something, I'm going to have a little relative, I'm sorry, at 1 and something, I'm going to have a little relative max. At 3 and something, I'm going to have a little relative min, so I better put max here, right? Otherwise, I'll be wrong, right? A max, and I'll put a minimum here. Now, if I put 1 into the original, I put it into the original to get the y value, and if I do that, I got 7, and then I put 3, and then I got 3. So I found my relative max and min. Now the next thing, I'm going to erase something. So if you need to, you have to stop, copy all this down, because I'm going to erase a bunch of this. I'm going to leave this up here. I think I'll erase this and all this here. And I'll leave my little relative max and mins. And I probably should write rel up above, right? Rel, relative max, rel, R-E-L, that's what that's supposed to be, relative min. And now I'm going to take the second derivative. And if you look at your first derivative, it's pretty easy to take the second derivative of that first derivative, and you'll end up with 6x minus 12. That's why I wanted you to copy it down, so you have to back up and get it. Go ahead. And of course, this is defined everywhere, so we set it to 0 to look for our critical points. And if you solve for that, you're going to get 2. So x equals 2 is a critical point. So you draw a line, a number line, and we're examining y double prime at x equals 2, and we're dividing it up. I put 0 in. I want to check what the sign of double prime is this way, and then I'll know where it's concave up, where it's concave down, and whether it's changing, and that's an inflection point. If I put 0 in, it's negative. That means our function, y itself, is concave down there because the second derivative is negative. And if I put like 3 in, I'll get a positive number. So that means my y, the original function, is concave up. And of course, since it changes from concave up to concave down, and this is a point 2 is in the domain of the function, this is an inflection point. So we have an inflection point at 2 something. Inflection, INFL, point, I'll abbreviate that, inflection point at 2 and something. And if you put 2 into the original function, you're going to get 5. Okay, so we have an inflection point. We also have a relative max and a relative min. We also know that it's increasing, 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 and then decreasing, and then increasing. So we know a whole lot about the function. And I advise you to write all this down, because now I'm going to erase this and graph it, right? I'll put my inflection point here. What is it? 2 and 5. And we'll quickly graph this thing. Won't be hard to do at all. So I'm going to erase all this stuff, accept our results, and I'm going to graph this. So, 1 and 7. So here's 7 here, let's say. Here's 1 and 7. That's a local max and an inflection point at 2. So it goes from concave down to concave. Let's see. What is it? Concave down to concave up. Is that? Yes. Concave down. I'm looking at my sheet here. It's concave down. So it's going to look like this. That's a little maximum there. And then 3 at 3. Well, this is 1, and this is 7. At 3 and 3, about right here, we have a little min. And we know from the first derivative that after 3, it's increasing forever. If you look at it, it's positive, like this, so it's going to go up like this. And by the way, there's a y-intercept at 3. That might be a little point you might want to plot there. And then, of course, it's concave down, and of course, it's increasing like this. So it looks like that, and that's our graph. And notice we got it just because we got these 2 points. And of course, we know how cubic goes anyway. It goes like this. It looks like y equals x cubed as x goes to infinity this way and infinity this way. So we should know that anyway. Lead term test, right? And there's our graph.